All right, let's begin by talking about volcanoes and tectonics. Uh, Volcanoes are a really great topic, very interesting, lots of neat things to discuss from the physics of the magma and the chemistry of the magma to the awesome power of the explosive eruptions and what eruptions can do to our atmosphere. Volcanoes are a really fun topic to talk about. So we're going to begin by talking about the largest continental eruption in the U.S., Mount St. Helens. And then we'll look at the Cascades, which are the mountain range that the Mount St. Helens is part of. And we're going to look at the tectonic settings at which we find volcanoes. We just finished talking about earthquakes and tectonics and the tectonic settings of earthquakes, finished earthquakes as a summary of them. We're going to talk about the tectonic environments of volcanoes to begin volcanoes. And so we're going to look at the different zones, including subduction zones, divergent boundaries, and hotspots. Here we go. All right, so let's begin by introducing with Mount St. Helens. All right, Mount St. Helens erupted on May 18th, 1980, and this was a major eruption. It was one we call a Plinian-style eruption that occurred right here in the northwest U.S. Here's a picture of the mountain before it erupted in 1980. It was a highly studied volcano because scientists knew that it was getting ready to erupt. It was bulging. Um, and there was much seismic activity going on as the magma shifted underneath the earth. Um, this observation post was actually destroyed, and the geologist at the site was killed in the eruption because we're looking at the mountain as it bulges towards us. So maybe they could have picked a better point to observe the volcano, but nonetheless, uh, volcanology can become dangerous sometimes. So this is a picture montage of what actually happened, noting that the bulge of the mountain here on the side from the magma moving forward caused a landslide. And when the landslide let loose, it released the pressure that was holding the explosive magma and gas in. And so it exploded upward and outward in this major catastrophic eruption. You can see Mount St. Helens here. Bef- uh, was as part of the Cascade. You can see Mount Adams in the upper left in the background. Sorry, upper left. It says upper right here, but in the upper left, looking west. Mount St. Helens was 9,600 feet before the eruption and only 8,300 feet after the eruption. So, 1,300 feet of the mountain just blew off. Steam blast began in March, indicating that the mountain was likely going to erupt anytime soon. They started monitoring the mountain, noted that the mountain continued to bulge as the magma moved towards the surface, like I said, and there were lots of earthquakes. Mount St. Helens was dormant for 123 years before it erupted in May that year. When it erupted, it sent material high up into the atmosphere that got caught up even in the jet stream. And the jet stream took that volcanic ash across the country within the next few days, creating quite an dazzling sunsets because of all the dust in the atmosphere reflecting and refracting the light. And the actual material that blasted out of the volcano went all the way across the state of Washington into the panhandle of Idaho. Here you can see in the dark red. Looking at the mountain closely, and this is right here where the actual volcano is, you saw a pyroclastic flow deposit. And this is a big billowing cloud of hot ash, gas, and air that blew out of the side of the volcano. And so that area is blown down there. Down timber zone extends out in this dark orange zone here. This is the sheer power of the blast blew down all the trees and scorched the entire area. The lighter tan here around the outside is the scorch zone. And then we have mud flows going down the river valleys because Mount St. Helens was snow capped. It's a tall mountain with snow caps. All that stuff mixed, all the ash mixed with the snow cap, created big mud flows. You can see the down timber zone here. Here are two geologists for scale. This area where a pyroclastic flow, the billowing cloud of hot ash, gas, and air came through and just completely blew everything away. The scorched land surface is shown here in the bottom right after the eruption, and this black area here, these are charred logs floating on a beautiful lake at the foot of Mount St. Helens called Spirit Lake. You can see this in the distance, Mount Rainier, the largest of the Cascade Range volcanoes here, um, looming like a monster in the background. There were also those mud flows I talked about were very deep and very formidable. Those are something that can completely wipe out an area. Volcanic mud flows are called lahars. It's an Indonesian word for mud flow after events occurring there, but you can see the damage it can do. Um, this is a steam blast from a smaller eruption and a lahar that was left behind afterward. This is Mount St. Helens in 1982. The eruption itself left a 1 mile wide horseshoe shaped crater on the side that it erupted from. This is our view from the northwest looking in on the volcano, just a completely devastating eruption. Mount St. Helens is one of the Cascade Range volcanoes. They go from British Columbia all the way down through Washington State, Oregon, and into Northern California, noting that they're slightly inland, but basically along the coastline. And they're very active. You can see the little volcanoes here indicating when the volcano erupted from 4,000 years ago to the present here, noting that there are some that are more active, Mount St. Helens being one of them. Mount Rainier being decently active, Glacier Peak further north in Washington being pretty active. In Oregon, the Three Sisters volcanoes, there are three of them that are near one another. Northern California, Medicine Lake and Mount Shasta, also uh, very active. You can see Mount Rainier being one of those active ones. It's the largest of the Cascade Range peak. Here it is pictured from Tacoma, Washington. Hopefully it doesn't blow this way because it would totally wipe out Tacoma. And then further to the west, you can see it from Seattle. Seattle is west of the volcano. This is looking east at Mount Rainier here, but it is near a very major populated area. The reason why we have these Cascade Range volcanoes is because the Juan de Fuca plate here is being subducted and shoved underneath the North American plate. Here's a look at it from the side, noting that when these subducted plates hit the mantle, the deeper they go, the hotter they get, and they begin to melt. Because these plates are waterlogged, they pick up a lot of water vapor, and the water vapor fragments the magma and makes it buoyant. And so as it rises at these subduction zones, you'll get volcanoes all along the coastlines. Cascades are one example. So let's talk about those volcanic zones, starting with these subduction zone style volcanoes. And these subduction zone style volcanoes are the most explosive that we have out there. In this scenario, the oceanic crust subducts underneath the continental crust because the ocean crust is a little lower and more dense. And again, as it hits that mantle, it begins to melt and send buoyant magma rising through the crust. The magma has high amounts of silica and water, which makes it sticky and gaseous, and it therefore explodes outward in these stratovolcanoes. There are two types of volcanoes that come at subduction zones. Those that come in the coastlines, those are called volcanic arcs, and those that have a oceanic subduction to form a volcanic island arc. Volcanic arcs are coastal volcanoes you would see in the Cascades. Here's an example from the Andes Mountains in Chile off the coast of South America. We have the Nazca plate being shoved underneath the South American plate here, and the oceanic continental subduction creates the Andes Mountains, and they are volcanic. Here's a volcano in Chile in 2008 erupting, just a really neat picture there. They are active. Japan is a great example of an island arc volcano where you have ocean plates subducting under ocean plates. And of course, there's no coastline for volcanoes, so instead they form islands. All these volcanoes all along the Japanese coastline are active and dangerous. Mount Fujiyama in Japan, Mount Fuji here, one of the large stratovolcanoes. This is what you think about when you think about volcanoes in your head, these steep-sided cones with these snow caps. We'll talk about this. This is one type of volcano called a stratovolcano. But these are island arc, and they come from oceanic subduction. All these subduction zone style volcanoes, typically, most of them hang out around this Pacific Ring of Fire. All along the rim of the Pacific Ocean, you have these volcanoes, and you have coastal volcanoes in South America and Mexico and North America here, along Alaska. And then you have these island volcanoes like the Aleutian Islands, the Kuril-Kamchatka Arc, the Japanese islands, the Philippines, all the way down through and into New Zealand down here. But you can see even in the along the Indian Ocean as well. This is the Pacific Ring of Fire because of all the volcanoes that occur there. And these are subduction zone style volcanoes, either volcanic arcs if they're on the coastlines, or island arcs if they are island volcanoes. Those are the most explosive, and we'll get into that more in their explosivity later. Suffice to say for today, we'll finish our tectonic zones with divergent boundaries and hotspots. Divergent boundary volcanoes are those that you would find where you have a spreading center. And typically, they're going to be at ocean areas or areas that would produce a spreading center in an ocean, mid-ocean ridge, something of the like, where you have the upward magma pressure pushing up, driving the plates back and down away by gravity, forming these volcanoes. And because the mantle comes directly from the magma comes directly from the mantle this time, it's not coming from melted crust. And so as a result, the magma is less, it doesn't have as much gas, and it's pretty runny and hot. And so these volcanoes are not as explosive. The type of magma you have is what we call basaltic magma. I'll get more into that next time, but it is hot, runny, high in iron and magnesium, and it's non-explosive. Iceland, of course, is one area above the ocean where we can see that mid-Atlantic ridge fountaining out the volcanic material, the magma. You can see it does produce actual fountains. They call them, lava fountains, and or curtains of fire as they squirt the magma up onto the surface, and it's pretty runny. The East African Rift Valley is another example. All those big deep lakes in East Africa, like Lake Victoria, Lake Tanganyika, those are all actually beginnings probably of what will eventually become seas and then ocean, because the crust is dipping down, it's starting to spread, and that runny, thin, iron-rich magma, dense magma, is coming up to replace it, creating low places where water fills. In Iceland itself, there are some examples of pretty damaging lava flows, or significant ones. There was one in 1973 that basically filled in a really important fishing harbor in Vestmannaeyjar, and about a kilometer of about a fissure about a kilometer from the town opened up and basically increased the size of the island by 20% as it spewed magma consistently into the harbor and elsewhere around. Pretty crazy. Here's the edge of one of those flows from 1973 in the town of Jaime. And our last type of volcanic setting then is hotspots. And hotspots can come in a couple of varieties, of those in the continents and those in the ocean. We, of course, know hotspots from Hawaii. Hawaii is a good example where heat builds up underneath a plate. It's usually in one little specific area, and it's fed by a steady conduit of magma from the mantle. And that magma burns its way through and reaches to the surface, forming volcanic island chains. And Yellowstone is another example you see pictured here. Same situation, just a very hot area under the mantle that kind of sends an active conduit of magma up. In the case of a continental hotspot, as that magma burns its way in, it has to burn its way through a lot of thick continental crust. And that thick continental crust is filled with silica. And so it makes the magma become very sticky and thick and explosive. So typically you'll find some big cataclysmic eruptions from some of these continental hotspots. But the Hawaiian chain, the current hotspot is located here. But as the Pacific plate moves northwestward, it created this entire chain over the last 50 million years. And prior to that, the Pacific plate was moving northward, and it produced these mountain chains. So this hotspot has been active for like 100 million years, nearly 100 million years. And here's the Yellowstone hotspot, currently in its location in northwest Wyoming. on the border of Wyoming and Montana and almost Idaho there. But you can see that the hotspot track tracks across the southern part of Idaho, producing these prior calderas, they call them, which are large craters from a major eruption. The Snake River Plain is one such area. There's an area here called Craters of the Moon National Park, and you can go and it actually looks like the surface of the moon because it's just nothingness. It's all cinders and ashes from the one of the past eruptions of this Yellowstone volcano. And those are our tectonic settings. Volcanic arcs, which is an example of which is Mount St. Helens and the Cascade Range volcanoes. Island arcs, Japan being an example, but Philippines, the Aleutian Islands as well. Those are explosive and they come from subduction zones and melted magma. Divergent boundaries are where you have mantle magma coming up and spreading itself across mid-ocean ridges with peaceful style eruptions. And hotspots, plumes of magma coming down from the mantle in the ocean sense, typically not as explosive. In the continental sense, burning its way through lots of continental crust to become explosive, but nonetheless another volcanic setting. So we will continue to get into volcanoes and their tectonic settings as we continue to move through our journey of volcanoes. We're going to talk types of volcanoes and the types of eruptions and then the volcanic hazards associated with them after we get done talking about the types of magma, both melted magma and mantle magma, and we'll get into that next time. So thanks for listening to Volcanoes and Tectonics.